The inverse of an equivalence relation is an equivalence relation. Okay, let's try to prove this statement. For this, what we'll do, we're going to begin by considering a relation R, which is an equivalence relation. So let R be an equivalence relation, and it is going to be an equivalence relation on the set A. Equivalence relation on the set A. In other words, what we are saying here, that R is a subset of the Cartesian product of the set A with itself. Now, what does it mean when we say a relation is an equivalence relation? It simply means that R is reflexive, it is symmetric as well as transitive. Our goal will be to show that its inverse of this relation, R inverse, this is also an equivalence relation. To show that R inverse is also an equivalence relation. So this is our goal. Fine. So how shall we show that R inverse is also an equivalence relation? In other words, in essence, we need to show that R inverse is also a subset of the Cartesian product of the set A with itself. So it's going to be an equivalence relation on the set A. Okay. First, we are going to check for reflexivity. Now, reflexivity states that if we consider an arbitrary element A, so let A be an arbitrary element in the set A, then if we say that A belongs to the set A, this must immediately imply that the ordered pair A, A must belong to the relation R. That's because R is an equivalence relation, which means R is reflexive. If it is an equivalence, automatically it would be a reflexive relation. Now, A, belonging to R would imply that A, must also belong to R inverse. All we have to do is, when we are defining the inverse of a relation, that means the elements within the ordered pair are going to get interchanged. Now, that also again gives us A. Now, by definition, A, belonging to R inverse simply means that the ordered pair A, is going to belong to the inverse relation R for all A belonging to the set A. So here what we have verified is that we have verified that R inverse is reflexive. This is a reflexive relation. Okay, so we're fine with the first part. Now we're going to check for symmetry. To check for symmetry, we'll again take help of the definition. The definition tells us that if we have an ordered pair A, B belonging to some relation R, then that should imply that B, A also belongs to the relation R. Okay, now in our case, what we'll have to show is that this is true for the inverse relation. Okay, for this, let us consider two elements A and B. So let A, B be two elements that belong to the set A such that we consider the ordered pair A, B belonging to the inverse relation R. Now, if A, B belongs to the inverse relation R, our goal will be to show that B, A also belongs to the inverse relation R. This is how, if we can show that, then the relation R inverse is going to become symmetric. Okay. Now, by definition, if we say that the ordered pair A, B belongs to R inverse, then doesn't it mean that B, A belongs to the relation R? Now, this is true because all we have done here is interchange the position of the elements within the ordered pair. So A, B belonging to R inverse also means that B, A must belong to R. Okay, now we have B, A belonging to R, but we have already mentioned that R is an equivalence relation. So if R is an equivalence relation, that means R is symmetric in nature. For symmetry tells us that A, B must belong to the relation R. Since R is symmetric, R is already an equivalence relation, so it is symmetric by default. So since it is symmetric by default, we are saying that A, B belongs to R, provided B, A belongs to R. Now, what we can say, if A, B belongs to R, then we can say that now we're going to interchange the elements within the ordered pair to get B, A, and now B, A must belong to R inverse, right? So what we have done here, thus, we have started out by considering the ordered pair A, B belonging to the inverse relation R, and we were able to show that the ordered pair B, A also belongs to the inverse relation R, and this is going to be true for all values of A and B belonging to the set A. So what does it tell us? This simply tells us that the relation R inverse is symmetric in nature. So this is a symmetric relation defined on the set A. And then finally, we're going to check for transitivity. So we'll have to use the definition. The definition for transitivity states that if we have the ordered pair A comma B belonging to some relation R, and we have another ordered pair B comma C belonging to the relation R, the same relation, it has to be the same relation, then it must imply that A comma C must belong to the relation R, and it has to be true for all values of A, B and C belonging to the set A. So here R is defined on subset A. Okay, now this is called the transitivity property. Now here we have to make sure when we are considering the two ordered pairs, the second element of the first ordered pair A comma B, which is B in our case, this must match with the first element of the second ordered pair B comma C. So only when the B and B matches, we can say that the ordered pair, new ordered pair A comma C belongs to the relation R. Now similarly, what we'll do, we're going to consider three elements A, B and C, which are being picked up from the set A, such that we consider A comma B to be belonging to the inverse relation R, and we are going to consider another ordered pair B comma C to be also belonging to the same inverse relation R, because our goal is to show that R inverse is a transitive relation. So that's why we're considering the two elements A comma B and B comma C to be belonging to that same relation R inverse. Now A comma B belonging to R inverse, we can also say that B comma A belongs to the relation R. That's by definition. And then B comma C belonging to R inverse simply means that C comma B belongs to the relation R. Now what we'll do, we're going to combine these two relations because both of the ordered pair are part of the same relation. Now here, if we look at the first ordered pair B comma A, its second element is A. Whereas if we consider the second ordered pair C comma A, its first element is C. So A and C are not matching. But what we can do, we can write the ordered pair C comma B first. So if we consider C comma B belonging to the relation R, and then B comma A belonging to the relation R, so now it's not a problem because now the second element of the first ordered pair C comma B and the first element of the second ordered pair, which is B comma, they are matching. Now we can immediately say that the ordered pair C comma A, this is going to belong to the relation R. So here we can see this because what? Because R is an equivalence relation, that means by default R is transitive in nature. So here we are using the property of transitivity for the relation R. Now if C comma A belongs to R, this should mean that A comma C must belong to the inverse relation of R. That's by definition. So what we have done here, so here we have shown that if we consider the ordered pair A comma B that belongs to the relation R, and we have another ordered pair B comma C belonging to R, the inverse relation R inverse, and B comma C belonging to the inverse relation R inverse, we were successful in showing that A comma C also belongs to R inverse, and this is going to be true for all values of A, B and C taken from the set A. Okay, so this confirms that indeed our relation R inverse is transitive in nature. So this is a transitive relation on the set A. So what we have done, we have successfully showed that our given relation R inverse is symmetric, it is reflexive, it is transitive, provided R is an equivalence relation. So we can say hence our inverse relation of R, this is also going to be an equivalence relation. It is going to be an equivalence relation on the set A, hence proved.